I am excited to kick off a new research project that I'm calling TinyScale Lab. In this video, I'll walk through the introduction, motivation, my research hypotheses, how I'm planning experimental design, what I'll consider success, the risks that I'm anticipating, what the final deliverables will be that I'll produce, and the timeline and budget. I'll also have a appendix section with some additional background information for those who are interested. The purpose of this project is to research the connection between training dynamics and model capabilities. This is motivated by two papers that I've studied in detail. First is TinyStories: How Small Can Language Models Be and Still Speak Coherent English by Ronan Eldan and Li. And the second paper is Small-Scale Proxies for Large-Scale Transformer Training Instabilities by Wortsman et al. Most LLM training related research requires a lot of compute resources that are financially out of reach for someone like me. At the same time, tiny models show emergent capabilities, which is what the TinyStories work showed, and they also exhibit large-scale training dynamics that the small-scale proxies paper showed. So what is the mission behind this work that is inspiring me? Well, I don't claim to be creating a definitive blueprint, but I do believe that this approach, using tiny models as proxies to study relevance phenomenon to models of all sizes, represents an underexplored path that could benefit other resource-constrained researchers. And I believe most researchers or potential researchers are resource-constrained. And I think this is how most of the world's potential researchers would need to work. Making ML research accessible to resource-constrained environments isn't trivial, it's essential for the field's diversity and progress. As a FastAI student, FastAI community member, democratizing AI has always been a foundational core value in my professional goals. So what are the research hypotheses? What are the questions I'm trying to answer? I've come up with 4 at this point, and this may change as I learn more about how things are working out. But the first hypothesis is that training stability directly affects specific model capabilities in predictable ways. Second hypothesis is that different model capabilities, like grammar or consistency, respond differently to training adjustments. Hypothesis 3 is that early training signals can predict which capabilities a model will or won't develop before training is complete. And finally, hypothesis 4 is that techniques that stabilize training will have varying effects on different types of model capabilities. I've kept these general at a high level because I really don't know what I'm going to learn, but I do have a sense, based on the TinyStories and small-scale proxies paper, that there is something around these 4 elements that I'm going to experience, and I expect to see some relationships. And that's really what this work is about. I want to bridge the TinyStories paper analysis on emergent capabilities, so grammar, consistency, factual knowledge, reasoning, etc., with the small-scale proxies paper training dynamics analysis. They look at things like attention logits. They look at training instabilities and how to mitigate them. And they look at 7 different learning rates and see how training at different learning rates affects these different output values like attention logits or loss or gradient norm or things like that. So what does my experimental design look like? I've decided for now that I'm going to focus on 4 model sizes, and this is very similarly following the TinyStories paper with the addition of a 120 million parameter model. So 3 million, 20 million, 60 million, and 120 million. I'm going to use the same learning rates as the small scale proxies paper, which is from 3e-4 to 3e-1 and 7 learning rates in total. I'm going to use the two stability techniques that the small scale proxies paper uses, which is QK layer norm and Z-loss. And these are direct responses to attention logit growth and output logit divergence, respectively. And what's going to be fixed across all these training runs are the data sets that I train on, the number of training steps, and other hyperparameters like weight decay and warm-up steps, and so on. The training dynamics that I'm going to log very closely throughout the training, and then I'm going to analyze them in detail, are the logits, the gradients, the parameters, and the losses. And I'm going to try to capture as much as I can. So I'm going to capture the norms, the means, the maximum values, and the RMS values. The capabilities that I want to evaluate for my models are split into three categories. And again, this is inspired by the TinyStories work. I want to measure foundational language capabilities, such as grammar and context tracking. And context tracking can also be thought of as consistency. I want to analyze and log and track emergent capabilities, which is factual knowledge, reasoning, and creativity. And finally, because this is TinyStories, I want to understand story-related capabilities, such as plot. So these are the 6 capabilities that I'll be focusing on, and the above line shows the 4 training dynamics that I'm going to be focusing on. And the relationship between these two training dynamics and capabilities is what I want to explore. So what will I consider success? Simple, but not easy. Establishing clear connections between training dynamics and tiny model capabilities. I think there are a number of things that could go wrong. I think there could be a lack of connection between these two, and I may find that, and that could be fine. That's something I will learn. There's going to be technical challenges in monitoring complex training dynamics. I might have a suboptimal parameter usage. There's always a balance of trying to get things to work and trying to get things to work right, and the amount of time and money you're going to spend in doing that. And finally, trying to get things to work fast and efficiently. And of course, there's always a risk that compute and inference costs could balloon and bloat beyond what's reasonable for me to complete this work. But I think I can mitigate a lot of that risk. Something that I've learned throughout the Fast AI course experience and being a member of the community is you want to shorten the iteration loop. And you want to ensure the evals are robust from the start so you get quick, immediate, robust, clear signal when you get feedback on how your model is performing. And I think I'm going to achieve shortening the iteration loop and anticipating some of these risks before they derail the project by starting at the tiniest scale and then progressively increasing size. I'll also implement early stopping, so if I don't need to run a training run for 20 epochs, then I shouldn't waste all that compute doing that. Even if in the moment it's only a few dollars, it'll add up over the course of the duration of this project. What am I going to deliver? What is my commitment to producing as a product out of this work? Well, the main thing is I want to have a comprehensive set of research repositories that include code, trained models, and detailed data sets. And these data sets will include the logging data for training dynamics, as well as the 6 different categories of LLM judge scores. I'll be producing weekly video content and blog posts, if not more frequently. I'll have a final technical report, and I want to create some type of data explorer where there are some interactive visualizations where you can go in and understand some of these relationships and play around with how you want to analyze that. And mainly, fundamentally, I want to do this publicly, and I want to do this in an open source way. So what's the timeline and budget? I think I'm going to break this up into 4 different phases. So phase 1 is eval and logging setup and initial training runs. I expect this to take 2 to 3 months. Phase 2 is the meat of the work. This is where I do all the experimental implementations. This is where I'm looking at everything that was taught in the TinyStories and small-scale proxies papers. I'm implementing that. I'm running these training runs. I'm logging the training dynamics. I'm evaluating the scores with the LLM judge. And I'm trying to understand what are the relationships in real time between training dynamics and model capabilities. So I expect this to be 3 to 4 months of work. Phase 3 will be analysis and synthesis, and this I think will take 2 to 3 months. And phase 4 will be documentation and finalization, which will be 1 month. So at minimum, I think this work will take 8 months, and it could go well past a year. The training budget is estimated on approximately 100 training runs. So I have 4 models, I have 7 learning rates, I have using QK layer norm and not, and then using ZLOS and not. And so those iterations together are about 100 training runs. And if I take my experience in the Tiny Hackathon, where I trained a 60 million parameter model for 20 epochs using an A100 GPU on Google Colab Pro, that was about 25 billion tokens across about 15 hours of compute, and that was about a little over $100. I'm expecting to, a little over $10. So I'm expecting to do 100 of these training runs. So I'm expecting conservatively, hopefully, the training budget to be $1,700. The inference budget, and again, this is very rough. If I am able to use Gemini 2.5 Flash, if it's capable enough to give me the type of LLM judge scoring that the TinyStories paper was able to do with GPT 3.5 or GPT 4, I estimate that the 224 million input tokens and 224 million output tokens, that is my conservative estimate, will cost $200. So the total estimate is $2,000 for this project. Now, that's something that's definitely worth an investment, because I do believe this project is going to open up a lot of insights and experiences for me that I think are just not possible right now. But at the same time, I also feel very privileged to even consider something like this as an independent, self-funded research project. And the other thing that I'm also thinking about is that at what point do I make the commitment and buy myself a GPU rig? If this is going to take $2,000, why not spend a little more or twice as much and get myself a GPU rig that I can own? So a lot of variables when it comes to budget and timeline. So I'm going to just take it 1 week at a time and see how things develop and make adjustments as necessary. So that is the core of my presentation. Again, the project that I'm working on is called TinyScale Lab. I think these tiny models are going to give me an opportunity to get some big insights about the relationship between training dynamics and model capabilities. Here are the 4 things I want to just use to recap this presentation. Again, I'm bridging training dynamics and model capabilities to understand what makes tiny models effective and whether or not those things are predictable based on how your training runs are going. I want to create a systematic framework for understanding how training choices affect specific model capabilities. This is what I'm really excited to see how, as they did in the TinyStories paper, how they saw that certain things like grammar and consistency were affected by certain architectural choices or training choices. I want to demonstrate that meaningful machine learning research is accessible with modest computational resources. Obviously, $2,000 is a lot of money, and I think I have to think hard and long about how I'm going to conduct this work so I keep costs low. And I think most important to me, I want to do this publicly, build publicly, research publicly, and open source all the models, the code, and my findings to enable broader participation in ML research. If someone with the similar interests as me, who's maybe 6 to 8 months behind in terms of what they're learning, if they see this work and it inspires them, or they can use something, saves them some time, saves them some money, gives them some insight, I mean, that would be truly the best reward that comes out of this work. I'll end the main section of this presentation with one of my favorite quotes that I think is really indicative of how I feel about this work, which is that you cannot be great without the greatness of others. And I truly stand on the shoulders of giants, especially these two papers and the authors involved. Without their work, without their contributions in the open source space, I would not be able to even approach this kind of research. So that's the main section. Now we'll kind of go into the after hours section of this kickoff presentation, which is the appendix where I want to walk through some additional background. So if you're not familiar with TinyStories and you're not familiar with small-scale proxies, then stick around and we'll walk through some of the main takeaways. So for TinyStories main takeaways, language models that are less than 10 million parameters trained on the TinyStories dataset can generate a diverse set of fluent and consistent stories that exhibit reasoning capabilities, knowledge of general facts, and the ability to follow instructions. Their GPT-4 teacher grading changes how we evaluate generated text. So we can have kind of these more subjective, kind of squishy, intangible type of scoring categories like creativity or plot for a generated story, and we can create a framework with an LLM judge. TinyStories trained models are not verbatim or simple template memorizing the training set. Grammar emerges first, followed by consistency, and finally creativity with model size. I am absolutely looking forward to witnessing this live as I'm training these models, as I'm evaluating them. I cannot wait to see some of these capabilities emerge with model size or training steps. Model depth is more important for consistency than for grammar. This is something that I may or may not dig into because I'm not going to run ablations as much as they did in this paper. Model width is more important for capturing factual knowledge, whereas model depth is more important for contextual tracking. Instruction following depends on number of layers. Coherence of plot depends on hidden dimension size. And increasing the number of heads, when that range is small, improves performance across all metrics. For the small-scale proxies paper, here are the main takeaways that I want to focus on. Attention logit growth is mitigated by using QK layer norm. Output logit divergence is mitigated by using zloss. We can predict large-scale instability learning rates by extrapolating small-scale performance. Lesser-known gradient RMS collapse is mitigated with a decreased atom W epsilon. And parameter growth seems to be causing the attention logit growth and the gradient RMS collapse for different reasons. For attention logit growth, because we have quadratic scaling of the parameter norm, if the parameter norm increases, the quadratic value of it increases even faster. And as we go deeper through the model, we have residual connections. So the parameter norm, as it increases through the residual connections, the final input layer's gradient is divided by, or the output layer's gradient is divided by the square root of the input norm. So that could be leading to this gradient RMS collapse. Things I won't be doing, and this was difficult to choose, but I had to limit the scope somehow of the research project. I won't be focusing on interpretability. That's more of a time issue. I won't be recreating the instruct model, so I'm not assessing instruction following capabilities of models. I'm not doing the number of layer ablations. I'm not doing the ablations for head dimensions. And then from the small scale proxies paper, I'm not analyzing the max attention logit instability threshold analysis, even though it's super cool how they did it. I'm not going to be doing attention scaling, LR scaling, pointwise attention, batch size ablations, or training step ablation experiments. I'm not going to be doing the scaling depth versus scaling width experiments, even though both papers have something to do with scaling depth and scaling width. I don't think that's going to be the focus of my work. And I'm not going to be not using warm-up and independent weight decay. Those are known interventions, so I'm just going to use them from the get-go. I don't need to prove to myself in that sense that those things work. We already know that those things are effective, so let's just use them. I will be doing generation diversity analysis, and this is something that was one of the more really, I mean, I guess all of that paper is really interesting, but this was one of the more novel things that I've come across. And they ask these different questions about generation diversity. So the first question is, how much of the new generation is contained in the original story? So they use a Rouge 2 precision between original completion and generated completion. So basically, how many bigrams are in the original completion that are in the generated completion? Then how similar are the generated stories to each other? So that's precision, bigram overlap between stories per story. To what extent are the k-grams in the generated story copied from the training data set? So what is the 2, 3, 4, 5 gram overlap between generated stories and the full data set's training stories? How similar is the generated story to its closest match in the training data set? So we're looking at the max precision between generated story and the training data set stories. And something that I want to add as a contribution to this line of work is doing semantic search using Answer AI Colbert Small v1 as a means of trying to capture the detection of complex template matching. So complex template matching is this concept where the model is not verbatim copying. It's not copying the story and changing the names of the people and entities, but it's copying some abstract pattern. Maybe there's something about the plot. Maybe there's something about the events that happen that it's copying in an abstract way. So that was something that they left for future work. And one thought I had as I was reading that was, what if semantic search can unlock this complex template matching? So this is something I want to do. It ties in with some other information retrieval work that I'm doing where I think there will be some nice overlap. So in this case, the query is the generated story. The documents are the training dataset stories. And I'm basically searching the document collection for a semantic search for the generated story, seeing what pops up, analyzing the results. Lots of really cool insights that I think could be gained, and just looking at the results will be really interesting. Something that I noticed during the Tiny Hackathon, which I dug into a little more, is that on the Hugging Face model and dataset cards, Ronan Eldan, the main author of the TinyStories paper, has left a lot of information in the discussion forums, answering people's questions. So I'm just going to read out some of this. They didn't use all the tokens in the dictionary when testing the model. The parameters indicated in the paper correspond to a vocab size of 8,000. So That's something I want to keep in mind. They took the GPT Neo tokenizer, tokenized the data set, and erased the extremely rare tokens, all but about 10,000. This was just for the sake of proof of concept that the embedding layer can potentially be made much smaller without affecting performance, but we did not implement this in the Hugging Face models. The models are actually a bit bigger than what is indicated in the paper, 10% for big ones, up to 40% for the small ones. We just tokenized the data set, and we took the top 10,000 IDs in terms of appearance. By no means those are the first 10,000, so the most common. And they also gave the recipe out. This was the 33 million parameter model. They trained it for 20 epochs, context length 512, batch size 80, 16 gradient accumulation steps, learning rate of 5 eneg4, weight decay of 0.1, betas of 0.9 and 0.95, and that particular file was used, and I think that is the 2 million or 2.1 million story dataset. And that's it. That's the end of my appendix. So again, I'm very excited to be kicking off this project. It's obviously in the very early stages, so I'm really doing this live as much as I can. So please follow along. I will be keeping everything in the TinyScale Lab playlist in my YouTube, and I will also have a TinyScale Lab tag on my blog. And if you're following me on Twitter and Blue Sky, you will definitely see a lot of posts on this TinyScale Lab project. So thank you for watching. I hope you follow the journey along the way, and I'm really excited to share what I find. See you next time.